Okay, so yeah, so physicists would fall into two camps. If you're gonna be, as I was saying, if you're gonna be a career physicist, you would typically either focus on the experimental side of things and be an experimentalist, an experimental physicist, sometimes called maybe an applied physicist, or you'd be a theoretician, you'd be a theoretical physicist. And they're similar, but different focus. Albert Einstein would be a classic example, or Stephen Hawking. They are theoretical physicists. They just think about stuff, right? I mean, they interpret the work that's done by experimentalists and try to make sense of it all. And you can tell the theoretical physicists by the massive frontal lobe, big foreheads, sparse hair from rubbing their head and thinking so hard. Usually their bodies have atrophied, so all their energy can go into their enormous brains. Not really, but that's their job. It's just to understand physics to the point where they can just sit around and think about stuff and try to understand the way things work. Experimentalists do something a little different. Experimentalists try to design equipment and or experiments using other people's equipment to come up with data in a way that's going to be very, very helpful to the theoretical physicists. They want to find data in a way and make observations in a way that enables people to say without a lot of conflicting variables, very clearly we can see that this is what is going on. So for example, hopefully, if it's funded, it should be funded. If we build the replacement to the Hubble telescope, which we're hoping to do, and I can't remember what it's going to be called, but it's going to be awesome if we build it right. It's going to be a space-based telescope that will have amazing resolution. We'll be able to, to look at various different wavelengths to the edge of the observable universe and really extract all this amazing information. The experimental physicists will be the ones that write the grants for getting time on that telescope and actually go in and set up the experiments so they can, in the tight little window of time that they have, they can get all the necessary information back that they can and kind of manipulate and, well, I won't say manipulate, they want to, take that data and compile it into a good, usable, readable form and pass it on to theoreticians who will then make good use of it. Does that make sense? We're going to be a little bit of both. We don't get to choose here because, when we're starting off with physics, we need to know how to do both parts of this. My bias is probably more towards the theoretical side of things. I think that for somebody in your situation, that's probably the most important part of it for now. And if you decide to go on in science, whether it's physics or something else, at some point, you'll probably confront this idea of which side you want to be on. You want to be a researcher, or do you want to be a theoretician, or whatever. You'll figure it out. We'll do a little bit of both, though. We're going to have an opportunity to do some really good labs, I think. And my philosophy is I would rather do fewer really high quality labs that are like more legitimately like college style labs than just do a bunch of corny high school labs. So we'll do some good stuff with the good equipment in there. I also want to do some kind of engineering type projects / labs. Something that we did in McMinnville that I always thought was really fun that my students just loved. We built trebuchets. So I'm thinking maybe we'll do something like that this year. You know what a trebuchet is? It's a gravity powered medieval siege engine, powered only by gravity. You got to be able to throw something as heavy and as far as you can. A lot of physics behind it. There's a couple different ways we can go with this. I'll kind of think about this a little bit. And we'll break into probably groups if we decide we want to do this and have all year to kind of work on these trebuchets. It's pretty fun. We'll go out some wheat field and see how far we can throw pumpkins or something like that. I don't know. But there's kind of fun stuff like that in physics where you get to build something, but there's a lot of thought that goes into design, and that thought is really going to be, articulated and informed by the physics that you're learning. I mean, there's definitely some physics behind how you're going to get this big catapult to throw something, or if we do, like an egg drop, I'll give you some limited amount of supplies, and you got to come up with some ingenious way of repeatedly dropping an egg from various heights, and you got to make it survive the drop. It's a fun challenge, but there's a lot of physics there. You got to build build this thing in a way where you're going to extend the impulse, thereby decreasing the peak forces acting on the egg. All that'll make sense to you pretty soon. So fun stuff. That'll be the experimental side. The theoretical side is going to be mainly just, we'll kind of talk about the theory of what are the models that work. I should be upfront with you and tell you that physics is really just, sure, it's probably the most fundamental science, and it's enjoyed the most success of any science in terms of its ability to predict. But having said that, it's just one big ongoing bald-faced lie in the sense that nothing is hardly ever exactly correct in physics. Really what it is, and many times, is just, it's a game that we play where we try to develop models that do the things that we need them to do, but maybe don't work for other things. As an example, off the top of my head, you've all had chemistry, right? And so you've talked about the various different models for an atom, right? Going back to, and I can't even always remember which one's which, but if we went to the planetary model, was that the Bohr model? No, that wasn't the Bohr model, was it? I can't remember. But the planetary model, where you've got, when you talk about, let's say, energy levels in a hydrogen atom. Remember talking about that, where the electron orbits the nucleus, and a lot of times you could talk about the radius of the orbit having to do with the energy of the electron, and it jumps between these levels to, does this ring a bell? Talking about like how it'll emit light when it drops down from one energy state to a lower energy state, right? That'll ring a bell. Is that the way an atom is? No, not at all. If you could shrink yourself down to a atomic level somehow, and you couldn't really use your vision then anyway, light wouldn't work, but say you could. Say we had like eyes that shot out little particles that, so we could resolve things on that scale. That's not at all what an atom would look like. Nothing like it. But is it useful? Absolutely. It's a very useful model. It tells us a lot about the way atoms really behave. And so it's still something that we use. Sure, we recognize that it's not perfect. It's not, it really fails in many ways to describe the way an atom is, but it's very useful for describing those changes in energy state, right? That's what physics does an awful lot. So, you kind of get used to that a little bit. It's not always as precise as you might hope it would be, but it just gets better with age as we accumulate more information. So the theoretical side is going to be, we'll talk about that stuff. We'll talk about the models that work, when they don't work. We'll kind of try to build some models from simpler models that explain things even better. More often than not, our models are going to rely on mathematics. So mathematics is really the language of physics. That's what enables us to really empower physics to make predictions as we harness it with math. We'll do some problem sets. I hope you like problem sets. I take great pains to try to make the problem sets interesting, but you have to sort of just prepare yourself for the idea in physics that when you do these problem sets, they're always leading up to better stuff. I mean, so if we're doing some kind of problem set where we're, on paper at least, we're dragging some object along a plane, an inclined plane, and we know what the coefficient of friction is and want to know how fast it's going to accelerate, that can seem kind of dry and boring, but that has lots of applications in real life. And think about what you're doing there. Yeah, that's a real world application that you're going to develop an understanding sufficient to make some really accurate predictions about what would happen. That's pretty cool. Just without seeing or just on paper, we're going to develop a sufficient expertise to where we can actually do that. We can predict how fast an object is going to fall if it's being, constrained by pulling an object via a pulley up an inclined plane. We can learn some interesting things. The direct applications, brakes on a car. How do we develop good anti-lock brakes on a car? It's all the same principle. We're trying to manipulate the physics in such a way, our knowledge of physics in such a way that we take advantage of the higher coefficient of static friction than kinetic friction. And we'll get to that stuff soon. It's kind of nice to know how that all works. Before we can do that though, we got to kind of wade through some dry, boring stuff. So we're going to look at kind of some tools that we're going to rely on for the rest of the year in physics. Whenever we measure stuff in actual quantities, like masses and lengths and whatever, we have to have some agreed upon way of describing those units, right? let's just kind of skim through this first couple sections together, and we'll just hit the highlights. I think that's sufficient. I'll give you a short problem set, but there's not going to be much to do with this. So let's start Chapter 2, Mathematical Toolkit. Yeah, the metric system, okay? In physics, we like to rely on what's called an MKS measurement system, which is not what we normally do in traditional Western culture, at least in U.S. Western culture. We have, for some odd reason, adopted a really stupid way of measuring things. You know, feet and inches and pounds and ounces, it just is, it's horrible. Why is it so bad? Why is the metric system so much better? The rest of the world uses the metric system, and it really is just way, way better. How come? It's easier to convert. How come?
Because it's by 10.
Yeah, it's all based on the number 10. Exactly. Everything is a multiple of 10. Powers of 10 and multiples of 10 are so easy to work with. But when you got to convert from, you know, from ounces to pounds to tons, oh my gosh. I mean, it just is, it's horrible. The math is just, in fact, it's so bad, it's very costly in some circumstances. You might remember, I don't remember exactly the year, but this goes back probably 6 or 8 years ago. Do you remember hearing in the news about NASA had sent a really expensive piece of equipment, a shuttle that was a probe that was going to land on Mars and was going to do some specific experiments, and then it was going to send back the data. And it's when we were really interested in knowing if there was any ice, water ice on Mars, and lots of looking for organic molecules in the soil and things like that. Really interesting, important stuff. And remember what the outcome was? Remember hearing about this? It went into orbit, and all of a sudden it just blipped off the radar. And people couldn't, and eventually they looked and we found where it had crashed into the surface. Why had it done that? The reason, after exhaustive evaluation and analysis of this, the scientists at NASA, these physicists, decided they found the mistake. The mistake was that one measurement was not properly converted from English to metric units. And if we had used metric units the whole time, it wouldn't have happened. And so that one little calculation error, it just rippled on down the line, and it caused the probe to think that it was much farther above the surface than it was, and so it cost, you know, millions of dollars and countless hours of all these physicists' work, you know, preparing these experiments down the tube just because of our stupid units. So I don't like them. So we're going to stick with MKS units. Meters, kilograms, and seconds are the base units. And then everything else in physics, every other kind of unit that we build for other situations is built from those base units. We'll have derived units. Just as an example, well, we measure velocity in terms of meters per second in physics, right? It's built from meters and seconds. If we want to measure force, instead of using pounds like we would in English units, we'll use newtons. And a newton is just a kilogram meter per second squared. So it's built from those MKS units. Measure energy, not calories. Calories are dumb. We use joules. The joule is just a newton meter or a kilogram meter squared per second squared. And these units all make sense to you in a little while. But notice the main thing here is they're all built from those base units, right? It works well. Prefixes. Just flip the page to 18 real quick. I need you to, within the next minute, you have to memorize. No, you don't. You don't have to memorize anything. I'm not a big fan of memorizing stuff. You can always look it up or Google it if you need it. I want you to know how to use it, though. These prefixes you will learn, you probably know most of them anyway, just from, you know, being people that have probably had an interest in science. And if we talk about base units, metric units, if I want to use a prefix of milli, what does that mean? A 1,000th. Yeah, so if I have a milliliter, it's a 1,000th of a liter. If I have a millimeter, it's a 1,000th of a meter. What is centi? 100th. Kilo. 1,000, good. So a kilogram is 1,000 grams. And I bet you even know some other ones. What about a mega, like a megawatt? Is how many, do you know? What do you think? I think I heard it whispered out there. Million, yeah. Mega is million, okay. What about like a megabyte? And a lot of times you can we think of this as computer storage, what's the next one up? Well, you go megabytes to gigabytes. So what's a gigabyte? What's a giga, you think? If a mega is a million, no, a billion. Usually we go in 1,000 increments. So it'd be a billion, a gigabyte is a billion bytes. And now most computers would even maybe have, terabyte. What's a tera? Trillion, yeah. Can you believe that? We're talking about computer storage. That's a trillion discrete bytes of information stored in this little magnetic drive. That's pretty good physics right there. That's applied physics. If we talk about really small stuff, milli is 1,000. If we talk about a micrometer, what's micro, you suppose? Millionth, yeah. Nano is a billionth, good. And then pico, trillion, we're getting really small. Nano is a number, you probably heard that. Maybe hear about nanoparticles. Sometimes if you ever read any science journals or you watch listen to NPR or the science news, you might hear about people talking about nanoparticles. The scale of the particle is nanoscale. That's pretty small. I'll tell you more about this at some point when it's applicable, but before I taught, I was an electrical engineer, and I did some specific work with focused ion beams and electron beam columns that worked with a bunch of researchers, and we would do stuff on that scale, nanoscale, where we're actually imaging samples at like the nanometer scale. Angstrom would be 10 times smaller than a nanometer. And that's another one you hear a lot of when you talk about atomic scales and angstrom. But these are just, you'll get used to these. I don't know all of them. I just know the ones that, like those. That's probably it. Only ones I know. If I need more, I'll look them up. So what happens, though, in physics when we deal with measurements using these units? And sometimes we deal with pretty extreme kinds of measurements. If we're measuring the mass of a desk or even a car, that's not that absurd. A car would be, a big Suburban would be, I don't know, 2,500 kilograms. That's not that weird. I mean, that's not a huge number. But what if we're talking about a planet, mass of the Earth? That's big. Mass of the Earth would be, if I wrote it down, if I remember it right, I think it's something like, would be a 5, 9, 8, and 22 zeros. That many kilograms. It's a big number. In fact, that's such a big number that A, I don't want to write it, and B, if I did write it, you just get kind of overwhelmed by the number of zeros, right? That's not a good way to write that number. It's a better way. Scientific notation. Now, I know earlier in life, there's a real dread of scientific notation because it's just not normal. But when you get to physics, you're going to learn to love scientific notation. Written in scientific notation, that mass of the Earth would be something like 5.98 times 10 to the 24 kilograms. That's good, because the best part of that is the times 10 to the 24 part. That gives you a really good idea about the scale of that measurement. A lot of times in physics, because we're approximating stuff a lot of times, and this is going to seem kind of weird to you, but a lot of times in physics, if we're doing these wild approximations, kind of shirt sleeve calculations that you could just kind of write down on a napkin or something, a lot of times we'll talk about that kind of thing. We feel like we're doing a pretty good job if we can get it within what's called an order of magnitude, meaning within a power of 10. That's usually pretty good. And if you think about it, I mean, talk about the difference between 10 to the 24 and 10 to the 25. Those are both enormous numbers. But if we can pin that down so we're getting pretty close to getting the right power of 10, we have a pretty good idea about the scale of that measurement, right? So scientific notation is huge for us. Very, very valuable. If we talk about things like the charge of an individual electron, that's really small. I mean, that would be something like 0.18 zeros and then a 1,9 or something like that coulombs. I can't remember if that's right or not. It's been a few years since I've taught physics, but I think that's pretty close to being right. That's another one. It's not convenient to write that number, and it's exhausting to even look at. But if we can see it in scientific notation, it has a lot of meaning to us, because we'd say 1.9 times 10 to the, I don't know if that's right, 10 to the minus 19, I think is what it is, coulombs. That minus 19 is huge. That gives us a real idea about the scale of that number. Okay, so they're very useful. There's a compact way of dealing with really big and really small numbers.
Now, how do we manipulate these things, though? This is going to be easy for you guys, not a big deal at all. But let's just go through a couple. Yeah, there we go. Let's go through maybe a couple. Oops, too far. That's what I want. Let's go through a couple examples, maybe involving the scientific notation stuff. So if I see a scientific notation number like that, if I want to write it in standard notation, how do I transition from scientific notation to the big ugly standard notation? Okay, move the decimal. How many places in which direction? 7 to the right, isn't it? Because that's a positive 7, meaning this is a big, big number, right? So I got to move it this way and add a bunch of zeros. Make sense? So I got to go, this becomes, there's my 3 and there's my 1. And I got to take that decimal from there, go 1, 2, 3, 4, 5, 6, 7. There's where it ends up. I have to fill all those places with zeros, right? That's the standard equivalent. Not very, pretty cumbersome. Okay, what about something like, you tell me, are these legitimate scientific notation numbers? Okay, I've seen some, I bet I know why. Here, let's change this one just a little bit. What if I make that a 6? Is that okay? How come that? It is. How come that's okay? How come? Okay, so the leading number, the number that's being multiplied by the power of 10 is, let's be very precise about this, is what? What are the criteria for that? Okay, between 1 and 10. Okay, could it be 1?
Yes.
Okay, it could, so not between then. We gotta be very precise with this, we gotta be physicists. It's gonna be, how would I say that? Greater than or equal to 1, and
Less than or equal to 10.
less, okay, but it can't be 10.
Less than 10.
Less than 10. There we go. Does that make sense? So this number has to be greater than or equal to 1 and less than 10. Good. It is. So we're fine. Now what if, this is a little weird, but would that be okay? It is. It's fine. Because it's written as some number that fits our constraints times a power of 10. This just means that we move the decimal how many places? 0. So the answer would just be 9.874, right? Another way of thinking about that, any number other than 0 to the 0 power always equals, called the 0 power property? 1. Yep, any number to the 0 power always equals 1, doesn't it? Okay. How about this one? Whoops. Is that one okay? Oh, no good. How come? Too big, right? Okay, how about that one? No good, too small. Okay. So, what if I wanted to, kind of lost track of what I was doing here a little bit. What if I wanted to write that properly? What might it look like? I'd have to move the decimal, wouldn't I? Which direction? Got to move it 1 to the right. So that would mean, essentially, if I move the decimal 1 to the right, am I multiplying or dividing by 10? Multiplying, right? I'm making the number out front 10 times bigger. So to compensate for that, what would I have to do with the power of 10? I'd have to drop it 1, wouldn't I? Right? So this would, I could rewrite that as 9.34. I moved the decimal 1 place, so that has to go down by 1, right? Times 10 to the 2. Okay, make sense? Okay. On a graphing calculator, a lot of times you'll see stuff like that, right? That would be our way of writing this number on, say, a TI-84. Have you done that before? So you just go 9.874, and then I think it's probably like there's a button. I think there's a button right on top, isn't it? It says, I'll have mine up here tomorrow. I just haven't done it yet. I'm sorry. You push a button, the EE button, and that's like saying times 10 to the 0. And the last number you push would just be the power of 0. Doing arithmetic with scientific notation, honestly, the easiest way to do it is just put it in your calculator and let it do it for you. And that's mostly what we'll do. I do want you to be familiar enough with it, though, that you kind of, at least in theory, know how to do these calculations without a calculator. So what if we want to do something like that? What if we want to multiply two scientific notation numbers? 2.3 times 10 to the 5th times 1.2 times 10 squared. I mean, obviously we could just put those in the calculator and let it do its thing, right? But how else could we do that? What do you think? Yes, ma'am.
Wouldn't you just times the 2.3 and 1.2 regularly and add the power 10?
Yeah, we do. And there's a good rationale for that. It makes perfect sense if you think about it, because oh, come on. There we go. Because how many numbers are we really multiplying there? I've got 2.3 times 10 to the 5th times 1.2 times 10 squared. It's just like multiplying a string of 4 numbers, right? Multiplication is associative and commutative, meaning we can mix it up in any order we choose and group them any way we want, right? So how about if we grouped it like this? How about if we said 2.3 times 1.2 times 10 to the 5th times 10 squared. Pretty slick, right? Oh. Time flies when you're having fun. We're doing physics. I'll put up a couple of really short assignments on Moodle. I'll try to get those up there tonight, but don't feel like you have to charge in and do them tonight. If you want to, if they're available this evening, you can try it. Otherwise, we'll just kind of finish this up tomorrow and go to the lab, okay?